Okay. So what I'm hoping to do today is to get to this statement of the Jordan-Holder theorem. Okay. So, okay, we have to define what a normal series is. So let G be a group. A normal series for G is just a sequence of subgroups G0 equals G, G1, G2, and so on, such that G1 is a normal subgroup of G0, G2 is a normal subgroup of G1, and so on. Okay. And not equal to G0, G2 is not equal to G1, and so on. Okay. Instead of all this notation, I usually write G equals G0, and then we have like a normal symbol. And so on. Okay. So this means that G1 is a proper normal subgroup of G0, G2 is a proper normal subgroup of G1, and on like that. Okay. Then we have a special kind of normal series. Okay. Let G be a group. Okay. A composition series for G is a normal series G equals G0, which is G1 is normal in G0, and so on. And then at the end, we have Gn, which is the trivial group. Okay, such that Gi mod Gi plus 1. So since Gi plus 1 is normal in Gi, we can form the quotient, and this is a simple group. Okay. Okay. And the Jordan-Holder theorem tells us essentially that a composition series for G is kind of unique. Okay. Well, it exists and it's unique. Okay. And this is like similar to prime factorization, which I will try to explain how. The example. Let's look at a composition series for cyclic group of order 30. Let's try and figure out what that should be. Okay, in order to figure out this, we need to know that all subgroups of an abelian group are normal. We also need to know that the simple abelian groups are cyclic of prime order. Okay. So let's find our composition theorem or composition series for C30. Okay. Right. G, which is a cyclic group of order 30, which is generated by X. And subject to X to the 30th is the identity. Okay. Now we need to find a subgroup G1. So this is G0. We need to find a subgroup G1. Oops, this is G0. We need to find a subgroup G1 such that G mod G1 is a simple group. G itself is not a simple group. Like it has a bunch of subgroups. Here are some of them. The subgroups of G. Well, they just correspond to the divisors of 30. So you have the subgroup generated by X, subgroup generated by X squared, subgroup generated by X cubed, by X to the 5th, X to the 6th. Let's see, we just need to enumerate all the divisors of 30. Let's see, next would be 10. And then we have X to the 15th and X to the 30th. That is the trivial subgroup. Now we have to figure out which of these subgroups gives me a quotient, which is cyclic of prime order. Okay, so let's just try this one. Okay, let's try G1 to be the subgroup generated by X squared. Okay, so what is G0 mod G1? Oh, I'm now seeing, okay. Thank you for telling me about this student. Something happened, okay. Okay, does anyone have any guess on what should G0 mod G1 be? Okay, I'll give you a hint. G0, that is a cyclic group of order 30. We can write it like this. X subject to X to the 30th equals the identity. G1 is generated by X squared. So when I mod out by G1, I'm saying, well, now X squared is the identity. So we can write G0 mod G1. Well, we can think of it. You can think that it is the group generated by X subject to X to the 30th is the identity. And also X squared is the identity. Of course, if X squared is the identity, this relation is trivial. This relation just follows from this one. Okay. In other words, G0 mod G1 should just be a cyclic group of order 2. This is a cyclic group of order 2. In other words, this is a cyclic group of prime order, so it is simple. Okay. Now, So we've kind of done the first step of finding a composition series. Now we have to find a subgroup contained in this G1 whose quotient is simple. So the subgroups contained in this group are basically all the ones where 2 divides the power. So that there's this one, and this one are all contained in it. But you can just try G2 to be this. Let's take G2 to be the cyclic group generated by x to the 6. Now, G1 mod G2 is generated by x squared, in which x to the 6 is the identity. So this is a cyclic group of order 3, it turns out. So simple. And then finally, we take G3 to be the trivial subgroup, because G2 itself is cyclic of order 5. Okay, so this is our composition series. Is just G equals G0, which is no, and x squared is normal in that. X to the 6th. And then we have the trivial subgroup. Okay, this is our composition series. And the quotients, G0 mod G1 has order 3, G1 mod G2 has order, or sorry, G0 mod G1 has order 2, order 3, and then G2 mod G3 has order 5. In other words, this is no coincidence. Since 2 times 3 is times 5 is 30, that's like the prime factorization of 30. So this composition series is really coming from the factorization of our group. Okay. Okay, so let's prove a proposition which says that composition series exist, and then we'll state the theorem about the uniqueness. Okay, let G be a finite group. And G has a composition series. Okay. So proof is by induction on the order of G. I guess to be clear, the base case is when the order of G is 1. The composition series is just G0 equals G. The composition series is just like this like one single subgroup, because the trivial group is the entire group. Okay. So this is the composition series, kind of like a trivial one. Okay. Now suppose any group of order less than n has a composition series. Okay. Let's take a group of order n and prove that it has a composition series. Okay. If G has no normal proper non-trivial subgroups. Then G is simple. Okay, now if G is simple, then we have our composition series is this. Because G, the trivial subgroup, is just isomorphic to G. G is a simple group, so this is our composition series. So we need each quotient to be simple, and G is already simple. Okay. Otherwise, suppose that K is a normal subgroup of G, and K is non-trivial, but K is not equal to G either. This is what happens if G is not simple. If G is not simple, we can find a normal subgroup that's like non-trivial. Okay. Now K has a composition series. Because K is not equal to G, so its order is less than G, so it has a composition series by induction hypothesis. So we can say like K equals K0, K1, all the way down to KR, which is trivial. Also, we can look at G mod K. G mod K has a composition series. G mod K equals G0 bar, G1 bar, all the way up to GS bar, which is the trivial group. And now we take each of these terms in the composition series. These are all subgroups of G mod K. So they correspond to subgroups of G which contain K. For each I, there exists Gi such that Gi mod K equals Gi bar. And then, so what we have is that we have G equals G0, which is normal in G1, which is normal all the way up to GS, and GS mod K is trivial, so that means GS equals K1, all the way up to KR, which is trivial. Okay, so by combining the two composition series, we get a composition series for G. I will admit there's some details I left out, which I'll try and fill in now. That is the missing details. Well, we need to check that GI plus 1 is normal in GI because the reason is that this is because GI plus 1 bar is normal in GI bar. Okay. Also, we need to know, is GI mod GI plus 1 simple? And the answer is yes, because GI mod GI plus 1 is isomorphic to GI bar mod GI plus 1 bar, which is a simple group. Okay. Okay, and then so, well, except for these details, that proves the fact that G has a composition series by induction, because this is our composition series that we wanted to establish. Any subgroup, like, yeah, because K and G mod K had composition series, G also has a composition series, and that's that is the induction step. And so we'd say by induction, G has a composition series. Okay. And now the Jordan-Holder theorem is the following. Let G be a finite group. Okay. Let's say that G equals G0, G1, all the way up to GR. And G equals H0, H1, all the way down to HS, or two composition series. For G, then the number of terms in each composition series is the same, so S equals R. And the quotients, G0 mod G1, G1 mod G2, and so on, are isomorphic up to reordering to the quotients H0 mod H1, H1 mod H2, and so on. HR minus 1 mod HR, GR minus 1 mod GR. Okay, and what I mean is that G0 mod G1 might be isomorphic to H1 mod H2. G1 mod G2 might be isomorphic to H5 mod H6. But each one of these quotients is isomorphic to exactly, well, not, but like each, okay. Okay, so this is a Jordan-Holder theorem. Okay, actually, today I wanted to stop there because just posted a link to that. Of course, you don't have to, you can just, but this form is just going to try and bring it up and share my screen. I hope I can share my screen. No, I can't. Okay, but that's unfortunate. Okay, but go to the form, fill it out if you have time. I'm going to look at the results over the weekend and take up the results on anonymous. Don't know who is posting what. Yeah, so please try it. I'm leaving this last 10 minutes of the class for you to do it, but I mean, it's completely optional. Okay. Okay, so so probably I'll try and do this at the end of every week. That's my plan anyways. If you want to know the motivation behind it, it's just because I'm in some, there's this class for teaching and learning And this is basically like one of the assignments is to try this. So that is what I'm doing. Okay. Anyways, in terms of class today, it's pretty much done. If you want to leave, that's okay. If you want to do the form, that's okay too. Okay. Okay, so that's pretty much it for me. Anyways, thanks for sticking with it. I'll talk to you next week. I really hope to finish marking the exam by next week. So I mean by Monday. That is my plan anyways. Okay. Yep. That's it. So I'm actually gonna stay signed in so that you can feel like, okay, that's it. Bye.